We're very happy to have Roji PS from IMSC, and he's going to tell us about emergence of diffeomorphism from QFT.
So this talk is based on an ongoing work with Adarsh Sudhakar. He's a PhD student at IMSC, and the project is still in the initial stages. So what is holographic principle? So this is something which is known to all of you, that string theory or a quantum gravity is described by a lower dimensional quantum field theory. And ADS-CFT correspondence is a concrete example of holography. Now, does this mean that we have a quantum gravity description for any quantum field theory? And which feature of quantum field theory give rises the additional dimension? Okay. In ADS-CFT, we have some understanding that the additional dimension of ADS can be identified with the renormalization scale. So there are so many people have worked on this. And given that, so can we obtain a dual quantum gravity description of a quantum field theory, a general quantum field theory, if there exists one, by solving the RG flow equations in quantum field theory? So let's review or just go through the non-holography, the quantum gravity description of conformal field theory on a d-dimensional sphere. So the statement is the following. So you have an equality between a conformal field theory and a quantum gravity. What is the equivalence? So it's an equivalence between a generating functional or function in conformal field theory and a partition function of quantum gravity. Okay. And the generating function of CFT on ST, and it has a conformal structure. The ST has a conformal structure H. That's like the source for the stress tensor. And this object is obtained by performing quantum gravity partition function computed by integrating over the bulk fields, all the bulk fields, including the metric, having a certain boundary value phi I0, and bulk metrics that have a double pole near the boundary that induces the given conformal structure H on the boundary. So this is the statement of the duality. So basically you have a d plus 1 dimensional ADS space here, and you perform path integral here that produces the generating functional in CFT. Okay. Once you have that statement, we can ask what happens once you do the Wilsonian renormalization. Okay. So we start from the UV of the quantum field theory and integrate out to a scale lambda. And this process can be identified with the integrating out of the bulk fields, including the metric between the ADS boundary here and another radial slice sigma b. And so if you choose a radial coordinate, you can naively think of the radial slice as some constant value for the radial coordinate. Okay. And this flow, so basically QFT RG flow equation is supposed to map to the radial flow equation, the bulk. So let's look in the quantum gravity side, what is actually happening. So we are integrating out the bulk fields between the boundary and another slice inside the ADS space, which I denote as sigma b1, and integrating out the bulk fields between the boundary and this slice produces a wave functional on the slice sigma b1. And it can be understood as a path integral in the region enclosed by the slice sigma b1. So basically you perform path integral inside with an appropriate boundary condition that satisfy the momentum constraint and the Hamiltonian constraint. If I think of integrating out, I impose the constraint just to make sure that the choice of slice is not actually a matter of like it should not be something which is very significant, because we know that we cannot have I mean, if you deform this slice, nothing should actually happen. Now consider another slice sigma b2 further deep in the
Naive question.
Yeah.
So we know what this path integral, what this wave function is, right? You would think of it, in fact, it's like some TT bar deformation, but with the wrong sign, right?
But there you have to impose a Dirichlet boundary condition, right?
But here also you're imposing a Dirichlet boundary condition on the slice in the interior slice, right? Aren't you?
No, so to begin with, I choose some values on that slice which satisfy like all possible choices, which satisfies the momentum constraint and.
It's the wave function. No, it's the same. If you take this to infinity,
Yeah.
then you will get back the CFT partition function.
Yeah, right. So this boundary conditions will be mapped to the boundary condition.
So then we can also get this by solving a Wheeler-DeWitt kind of equation with some. I mean.
Yeah. So that's what you mean by like flowing it, right?
Right, and that's like some TT bar deformation with some wrong sign. I'm not quite, but
yeah.
But is this exactly the same as renormalization, because that is very precise, right? So is it
like
really the same that if you integrate out an energy shell, you will get the same
answer? No, I'm nowhere
answer?
saying that this is not that. I'm just trying to understand it. Like I want to see whether this thing can be repeated in an arbitrary quantum field theory. Let's say some scalar field theory, and what do I get?
Energy slices, do we know whether it's really the right thing to do, or is it just something, I mean, will it really give us this quantity? Like doing renormalization?
Yeah, that's what I'm trying to understand. So this is a statement. This is how we actually try to understand. Like you do Wilsonian RG, and that corresponds to integrating out bulk fields in the bulk quantum gravity. Yeah.
So this seems to be the same setup as the Himskak-Polchinski or the Faulkner-Liu-Rangamani, the double trace flow setup, in which this can be explicitly calculated, and the beta function equations can be compared with the Hamilton-Jacobi equations.
Yeah. So basically, that's the kind of thing that people do in this area, right? So you have a Hamiltonian-Jacobi formulation of RG flow, and that is mapped to the Hamiltonian-Jacobi equations in the bulk,
which can be mapped with which can be compared with the field theory beta functions.
Right. Exactly.
Yeah. That's right.
Witt equation.
Yes. You have to add the double trace.
Here I'm not seeing the double trace. That's what is worrying me.
Oh.
Did you add double trace somewhere?
No, actually, this is like schematic. Like I haven't done, this is not something which I'm taking it like a computation. So what is the thing which is happening? So because at the end, I want to just stay in the quantum field theory and identify what kind of operations that I'm supposed to do, which may give me some higher dimensional theory. There's something like, so you should not take it too seriously. Okay. So this integrating out bulk fields give you wave functionals on slice sigma b1 and another slice sigma b2. Okay. So naively, like if these are like wave functionals, following the statements in quantum mechanics, one can say that one wave functional can be mapped to other wave functional through a propagator. Okay. So you have the propagator K that relates the wave functional psi b2 to psi b1. Okay. And so the thing to notice is that on slice sigma b2 you have a particular boundary condition, and on b1 you have another boundary condition. So if you integrate out the boundary conditions that you have chosen, like in this sigma b2, so that will take you to the wave functional in the bigger slice. Okay. So it's basically like gluing of partition functions or cutting of partition functions in any quantum field theory. And the point is that the propagator, which maybe we can call as quantum gravity propagator, can be understood as a path integral that you perform in the volume nu bounded by the slice sigma b1 and sigma b2 with appropriate boundary conditions. Okay. So the main point is the quantum gravity propagator can be identified as a path integral in a region in the bulk or in quantum gravity. So now we can ask, is there a RG wave functional corresponding to the quantum gravity wave functional? Okay. So if I take the slice sigma b1, so this slice to boundary, we know that there is a wave functional, and that is the generating function, right? And we ask, is there a RG wave functional that is dual to the other slice. So let me call sigma b2 as sigma b. So the wave functional on the sigma b, can I identify with a corresponding RG wave functional in the boundary theory? So that is equivalent to asking, is there a RG propagator R dual to the quantum gravity propagator K? So, if there is an RG propagator, is there a path integral description of this RG propagator? So, if you can identify that path integral, is that a d+1 path integral of a d+1 dimensional theory? Okay, and people had made attempts along this direction. So, I would like to see in a scalar quantum field theory. No, I haven't identified it. So my question is, you know that there is a quantum gravity propagator which has a path integral description, which is the path integral for a higher dimensional theory, right? Now, do we have a, so if you map flow, RG flow to the radial flow, I can also ask, do you have corresponding wave functional and corresponding propagators, right? And if this mapping is exact, then the RG propagator should be describing the quantum gravity path integral that you do between two slices.
Difference from Himska.
No, it's the same thing, but I just want to see, like, any quantum field theory, if I repeat it, let's say I have a quantum field theory for which I don't know whether there is a gravity dual or not. So if I run there all these people's argument, if I run these arguments in a general quantum field theory, take a scalar quantum field theory, do we have similar structures arising there? Okay, and can I identify a propagator, and can I identify a corresponding d+1 dimensional theory, or at least in principle what should I do? And let's say if I find some fake path integral which describes some d+1 dimensional theory, can I impose diffeomorphism invariance for that theory? And will that constrain my original theory? So that way, is it possible for me to come up with a set of constraints that tells me a particular quantum field theory has a dual description? Yeah. Yeah. So basically, even in RG, that's what I'm putting as a constraint. Like, you know that changing the RG parameter won't matter. So through the RG equations, that's taken care. Now, if I try to mix the RG direction with the physical coordinates, then there is no way, I don't know whether such a diffeomorphism exists or not. But if I can construct a d-dimensional, d+1 dimensional path integral for the RG propagator, there if I can demand it. And demanding will or may put some constraint on the Wilsonian effective action.
But there's really only one part of the bulk diffeomorphisms that's physical. That's the Gauss law, which has to do with large diffeomorphisms. Yeah. All the small diffeomorphisms are just redundancies in description.
Right.
So it's worrying me that you're treating it as some kind of symmetry that you should impose. It's not a symmetry that you should impose.
It's not symmetry, right?
Or any constraint, right? It's just some redundancy. You chose to use a redundant description.
If I just start with a quantum field theory and do the usual physics that we do, can I end up with such redundancies? Like if, I mean, but
so redundancy is something.
Redundancy in the sense, like if I mix the coordinate, the physical coordinate, let's say my quantum field theory is defined in a d-dimensional space with some coordinate y, a, and a runs from 0 to some d-1. And if I try to mix this coordinate with the RG coordinate, basically the scale parameter, will there be a symmetry? So this is something which I don't know. I hope that may put some constraint, right? So in the usual ADS-CFT, that should be the thing which is happening. You get a RG direction which can be mixed with the original direction of your CFT. And still, that higher dimensional theory that you construct out of this RG should have the gauge symmetries, the diffeomorphism symmetries, right? So that you have a quantum gravity description. So I just want to start with a scalar quantum field theory. And so there is only one field, but action is not known to me. It can have infinite number of interactions. So just take that action, and S is the action for the scalar quantum field theory, and there is only one field O, and I'm considering the generating functional. So by introducing a source phi 0, okay, for the operator O. Now assume so let's say this is the starting RG wave functional, which is the generating function, like in the ADS safety picture. Now, so let's assume that there is a RG wave functional, psi bar lambda, and that wave functional should be a function of a new source, which I obtained from the original source by RG flow. So this is something which I have to understand. I don't know whether this such thing exists or not. So basically, I should be flowing my source also. Somehow the source also should flow, right? And if such a wave functional exists, then I can start from that wave functional, which is defined at some scale lambda, and then maybe there may be a propagator also. So take that propagator, multiply with the wave functional, and perform path integral over the modified source. So that may produce the original wave function with which I started, basically the partition, the generating function of the CFT. Now, if I want to identify this structure, what I should do is that I should be able to take this generating function, which is written here, and express this object in this form. Basically, I perform the Wilsonian RG and then identify a form similar to the one that is proposed here. So basically, you can perform you can take your fields and split into the high energy mode and low energy mode, and you can run the usual integrating out procedure. So so what we do is we consider a cutoff or a scale lambda, and assume that there is a bunch of field that has mode of p less than lambda and mode of p greater than lambda, and I do this divisioning by introducing a delta function by stating that the field which is lying on the shell, mod of p equal to lambda, is equal to some value O lambda, and then integrate over the O lambda. So this way I can identify what are the fields that is lying above the shell, below the shell, and on the shell. Okay. So now, sorry, lambda is just some parameter, right? And so now this delta function can be replaced by a path integral by introducing an auxiliary field chi. Okay, so this is a trivial step that you do. And now one can perform or integrate out the modes which is above the scale. This is something which you can do. Okay, so what you will get is precisely this. You perform or you do the integrating out, and instead of the action S, you will get a modified action, which is the Wilsonian action, with a modified argument. When you perform this path integral like by hand, this is what you get. Now you can declare, so you can identify a source which actually or some an RG evolved source. So the structure of the partition function or the function is such that when you perform this integral over high energy modes, it actually gives you a function of phi p, which can be thought of as RG evolved source. And why I call that as an RG evolved source? Because if I assume that if I don't do RG, then this field matches with the original source phi 0. So that's why I think that this can be identified as an RG evolved source. Okay. Now the argument of this S lambda may look weird because I have introduced a delta function here. So that's just a formal thing. what you can do is you just look at the expansion of Wilsonian effective action. So basically, so you have the elementary interaction in the Wilsonian effective action, and then insert the field configuration, then integrate over the momenta, right? When you do the integral over momenta, so what you will do is this delta function will restrict you to the shell. So you don't have to worry about the delta function here. And there are this derivative over phi lambda. So I should tell you what exactly is phi. So so you have field O. You split that O into OH and OL. OH is the high energy modes and OL is the low energy mode. And take that OL, multiply with the inverse of the propagator, and add it to the source with which you started. So that provides you the RG volt source. So now this structure of the wave function of the generating functional is very close to what we proposed, right? So we propose that we have a wave functional psi bar 0 and propagator and another wave functional, right? This is the one which we proposed. So we wanted to convert the the generating function into this form, and by introducing this delta function and by integrating out, what we achieved is we got a form of the generative function which looks exactly like the one that I wrote. So from here I can at least identify what is this object, product of propagator and the proposed RG wave functional. Okay. So we identify R into psi bar lambda as this integral. Now, so we have identified a product of propagator and a wave functional. So now we should remember that the object that we started with, if I just do the Wilsonian RG, that produces the Wilsonian effective action in the low energy mode, and this satisfies the Polchinski equation, right? Now we can ask, what is the effect of this Polchinski equation on this object? So the claim is that this Polchinski RG equation becomes a Schrodinger equation in scale lambda and in the modified source phi lambda. So that looks really nice. So you started with set of fields, you performed the RG evolution. Along the RG evolution, the source also changes, and that source, in terms of that source, you are able to identify a Schrodinger equation. Now, once you identify the Schrodinger equation, you can read out the Hamiltonian written in terms of the modified sources. Now, once you identify the Hamiltonian, you can perform a Legendre transformation and convert the propagator into a path integral. Okay, and that path integral has the basic variables are the original coordinate of the space-time where you defined your quantum field theory and the scale lambda. So it's actually a path integral for a d+1 dimensional theory. Okay, so you can think of the propagator, RG propagator, as a path integral for the modified sources, which has elementary, like it has actually it is living in a d+1 dimension space. Okay, this is something you can do even in a scalar quantum field theory, and then you can ask the action that you obtain whether it has the symmetries under or the gauge symmetries under the local transformations. Basically, if I change tau to some other parameter, it should not matter. Polchinski equation itself guarantees that such a change, variable change, won't affect anything. So that is not something, not a surprising thing, or not something which is. No, I haven't. I'm nowhere talking about ADS. I'm just starting with a normal quantum field theory. Yeah, because it's just that the coordinate lambda is the scale parameter, which actually kind of together with the origin. I don't know the metric. So for that, that's the second step. So first I have to see whether there is a Lagrangian, higher dimensional Lagrangian exists or not. And from there, I can demand that under coordinate transformation, this Lagrange should be invariant. Even in usual general relativity, if you start with the Einstein-Hilbert action, just demand this invariance that will produce the Hamiltonian constraint and the momentum constraint. From that, you can read out what are the the Hamiltonian constraints and the momentum constraints. Like that tells you what are the elementary variables of your theory, right? The momentum and the metric can be identified from there. So I just demand this invariance, and then from there I can try to read out what are the Pi's and the GABs. So that I haven't done yet. So I was saying that if you rescale your RG parameter tau to something else, that should not affect your theory or any description, because that is guaranteed by the RG flow equation. Now, what is non-trivial is if you try to mix y coordinate, which is the coordinate of the spacetime where quantum field theory is defined. If you start mixing the actual coordinate of the spacetime and the RG parameter, now do you still have the invariance? Now, the point to note is that the Lagrangian that we are proposing, which can be written in terms of the Wilsonian effective action itself of the original theory. So one should be able to precisely figure out what exactly is the form of such a Lagrangian. So, yeah.
I'm not understanding this, because this is, you're assuming that somehow, I mean, diffeomorphisms are realized as mixing of the scale and the coordinates. I don't think that, I mean, is it clear if you take n equal to 4 Yang-Mills, which we know as a holographic dual, and you do this, you do RG flow, and then you mix these coordinates, and that you'll get the same answer? Like, it's not clear that the n equal to 4 is invariant under these kinds of transformations.
It's not clear to me also. I just asking whether that's if you are identifying the scale with the radial parameter, what else are you doing?
Maybe you shouldn't be, I mean, maybe it's some gauge invariant answer, that because on the boundary you're doing something that's gauge invariant.
If it is there or not, that's the thing which you have to check, right? If it is there, then I can't prevent it, right? I'm nowhere saying that it should be there. I'm just saying that if it is there, what will that constrain the Wilsonian effective action? So I'm nowhere assuming anything. It's just that if it is there, then what kind of Wilsonian effective action that theory can have?
It should be, right? It's this Friedel-Wheeler-DeWitt equation, radial Wheeler-DeWitt equation. But again, it's not clear to me that you're getting that. There's a very specific equation which you get, which is the radial Wheeler-DeWitt equation, which evolves the wave function in the radial direction. But I don't think and that's also related maybe to adding this double trace term. It's not clear to me that we are getting this here. I mean that this...
No, see, the point is that I am adding sources. So you're supposed to add sources for all the operators in your theory, right? So including not just one particular operator. So the statement is that you should be adding all the sources. Now here this is a toy model where I'm just showing that, see, the structures are like very similar. So in no way I'm saying that you should not add certain deformations. Let you add all the deformations, see what happens. So I can do that in a toy model, right? In a scalar quantum field theory. Why should I look for very complicated theory? Even in the scalar quantum field theory, am I getting something or not? Exactly. That's why I'm saying if I impose the kind of coordinate transform, basically those are the one corresponds to deforming the slices, right? So basically you can assume that you start with the Gaussian normal coordinate, do a particular coordinate transformation that will introduce the lapse and the shift. Right? Since here I don't know what is the metric of the space-time, there is no point in asking about the lapse and the shift. So I have to impose everything through coordinate transformation, which I can anyway do even in gravity. I don't have to go for shift and lapse, right? I can always stick with the coordinate and then do whatever I want. So I just want to do that and see what is I can identify what a momentum constraint is actually supposed to generate, right? So I'm just demanding the same thing in quantum field theory, same coordinate transformation. What will be the result? What will be the Hamiltonian associated to these transformations? And set them to 0. So that will be the one which actually producing the momentum constraint and the Hamiltonian constraint. Now the non-trivial thing is the relation between momentum constraint and the Hamiltonian constraint. Like momentum constraint is like di pi ij equal to 0, and then the Hamiltonian constraint has pi ij. So the particular combination plus that curvature of that slice, right? So all those things, am I able to? Will I be able to reproduce? Right. So that's the thing which we have to see, whether the structure of this invariance has anything to do with the gravity structure. So from there, maybe one can identify. So basically, I started this project to identify what is the realization of Raychaudhuri equation in dual CFT. So there, I had to identify like what is the variables, like the extrinsic curvature, how that looks in CFT. So
maybe lambda is not R itself.
sorry.
What if lambda is not R?
No, then fine. Like I will learn it, right? So there are claims. So I am no ways assuming anything. I'm just saying that if that is the true story, things should work as in gravity, right? The higher dimensional theory you get out of RG flow should work like a gravitational theory. Otherwise, then why should you make a claim like RG flow is exactly equal to radial flow? I just want to understand that claim. I am no way partial to anything.
So Roji, this old, sorry, just one question. The old Friedel, Laura Friedel's paper, I think Suvrat is referring. So the radial relativity equation was conformal void identity.
Yeah.
But what about the momentum constraint? Did he have anything about?
No, I don't. I don't know. So
okay.
Again, those are like another set of void identities, right?
Yeah, but that's just invariance of the source is just invariant and the boundary.
Yeah.
It's integral of the boundary.
So my impression is that all like when you have a CFT, you can do this flow by just looking at the anomaly terms, right? Which has general structure. So here, that's why I don't want to look at, like just to understand the basic story. Don't take a CFT, just take a quantum field theory. What are the structure coming out of it? Because there I cannot use this easy tools, right? So just do the usual Wilsonian RG and see from there, like we can do those physics, right? These are things which you can calculate. As a functional integral, just perform those simple integrals and see. Like here itself, like when I do this earth integral, this integrating out, it actually produces a structure where I get a description of the theory written in terms of the modified source or the RG Wald source. That itself is a nice thing, right? In fact, in gravity, like ADS-CFT, that's what should be happening, right? The description should be converted into the theory of sources, right? So here, I had no expectation that the partition function or the generative function, once I do the integrating out of high energy mode, will produce me or give me a structure like this. So it is natural to go further and ask more and more things. So that is my philosophy. Yeah, so I want to identify this Lagrangian for the higher dimensional theory, and then demand that this Lagrangian has has invariance under various coordinate transformation, and from there identify what are the constraints. Now, since I was keep on saying this Lagrangian is constructed out of the Wilsonian effective action, so that may put constraint on the Wilsonian effective action. So which we can try to see. Like let's say I do the same thing for a value of lambda which is very close to 0. So there I can do perturbative RG, which is solvable. Like when Polchinski himself had solved for like the completely solved phi4 theory, right? So I can take a theory where like this is done. So then I can see like demanding these constraints, what that amounts to. So is it possible to like utilize this? Anyway, people are trying various things to constrain things, right? So let's try this also. So that is my goal. So can we, and the point is identify that constraint, and we ask, can we solve this constraint and identify quantum field theories that have a QG or a description where you have diffeomorphism invariance. Sorry? This is exact RG. Polchinski equation is for exact RG. No way is saying that theory is weak or strongly coupled. So what we are supposed to do is just functional integrals. If you can do it, that's it. See, the point is that here, I just claim that after the, I mean, when you perform this high energy mode to high energy mode integration, I'm just using the definition of Wilsonian effective action. So this comes out. Like you have a definition for Wilsonian effective action in terms of functional integral. It is known. Like, and that's precisely what Polchinski had used to derive the Polchinski equation. So I'm just using that technology and see whether we can push it. So instead of like, anyway, so many fancy things we do, so just do the usual physics and see whether we can get all the thing that we know out of it. That's it. Thank you.
Maybe just one question. So the last one about YA, diffeomorphisms and why are the boundary coordinates?
Yeah.
So you want to look for generally covariant theories on the boundary somehow? Or,
No. The point is that this transformation, this epsilon vanishes at tau equal to 0.
Okay,
right?
okay.
Like in gravity. At the boundary, you don't impose the general coordinate invariance, right?
Okay. Epsilon is vanishing.
Epsilon vanishes at tau equal to 0. So maybe you can consider another transformation where tau goes to tau plus y, ya some trace with some other epsilon a.
These are also very restrictive from that perspective. Like epsilon a could be arbitrary function of tau. And
Yeah. So that's how like that actually give you a general invariance, right? It's not like identifying the isometries of the spacetime.
I seem to remember some work by Sang-Sik Lee, which so he tried to first get the ADS direction as the RG directions from spin models and very simple condensed matter systems, stat-like systems. Right. Later on, he had some other papers, I think, using lattice field theories and trying to get diffeomorphism out.
Yeah, I have seen like many references since I like I said, I'm not an expert, so I'm not able to understand many of these things. So I thought just start with a usual simple scalar field theory and see like what we get.
Very confused what it means to get diffeomorphism. Let's say we take the Ryu Takayanagi problem.
Yeah.
It's giving you a gauge invariant quantity on the boundary. It's giving you a gauge invariant quantity in the bulk, which is some area. Now, what would it mean to get diffeomorphisms out of that formula?
I understand. Like in the ADS-CFT, you don't have to say that a non-gauge invariant object should be mapped to the CFT. Right? There is no demand like that.
Exactly.
So I'm just saying that whether it comes out or not.
But don't we expect it not to come out because we want the CFT to have only gauge invariant quantities. Now what you're saying is you want a redundancy the CFT has only, and what you're doing is also gauge invariant, right? If you do this,
right.
Then
the Lagrangian is also gauge invariant, right?
Everything is gauge invariant on the boundary, right? Yeah. So why would you expect bulk redundancies you said there's a bulk Gauss law which is physical, right. But bulk redundancies in description?
No, actually see, the point is that I construct a Lagrangian. And I'm just asking whether that Lagrangian is invariant under transformations or not. Yeah. No, this varying the taus are I like.
Lattice cutoff or the momentum cutoff is the what?
Now, what is varying is
T tau going.
Is y as equal to y plus epsilon tau is there absolutely because you are allowing for coupling constants that depend on the spacetime on the boundary spacetime form. And somehow you want some diffeomorphism that mixes that with tau. I don't see it being careful, but there is some redundancy. It just independent of tau. Like that maybe.
Yeah. You are talking about the local RG. Yeah, exactly. Yeah, locally varying your RG parameter.
Just to build on Gautam's and Ashok's comments, actually there's a series of papers by Vasudev Shyam, where he actually gets shows that under certain assumptions, the West-Zumino consistency conditions of RG in the boundary actually become the Hamiltonian and Diffeomorphism constraints in the bulk, and you
But
get the full.
Isn't this what Laura also showed in his paper in 2007, 2008?
I think
Suvrat will know, right?
Most of the work actually, I think along that line looks very similar, like basically inspired from this Friedel's and some bunch of people, like some initial papers are there.
Construction which had
I think Vasu's construction is a little more general than Friedel, yeah. Yeah, so this is what do you say? These West-Zumino consistency conditions are about not about boundary anomalies, but about consistency of local RG flows, doing local RG flows in different ways. So yeah, I can't reproduce the actual flow of logic in the work.
Yeah, so basically, I think those are like inspired by the work of Osborne. Like he's the one which actually classified all those, like the kind of RG that you're.
Okay,
so
yeah,
even Vasudev and all, like they are taking result from that. So I am familiar with Osborne's result. So
yeah. Okay, I thought you were building on Sangsikli's stuff. Yeah. I think that's the physics outcome, but again, I don't remember the papers very well. Yeah, sure.
But I think just to ask, follow up with Ashok's question also, but the scheme, I mean, the observable correlation functions will be scheme independent, right, Ashok? I mean, so somehow, okay, I see. So I think then you would only see it if you somehow can construct a Lagrangian.
right. Yeah. I mean, I'm just saying that the Polchinski equation can be recasted in such a way that looks like a Schrodinger equation in terms of the couplings or the basically the sources.
What Suvrat is saying is also consistent because he's looking at correlation functions of boundary observables. They will be scheme independent.
Yeah,
so they will not see this.
Yeah, in fact, the flow equation is coming out of that, right? You demand the invariance of observables under your scheme and all those things. Right?
Question?
It's not more than that.
Question like in can I ask like in QM at least you don't expect any running, right? So how would you interpret 2D gravity this way? Like
sorry?
In QM, like you don't expect running, right? Like RG in this sense, like, or am I confused? Yeah.
No, actually I'm considering a quantum field theory and then doing a Wilsonian.
Yeah, but like you could still argue 2D gravity should work this way, right?
I don't know, I haven't tried.
So couplings can run.
Oh, is it? Okay, then I'm confused.